Should I start? All right, hello everyone. I'm here today to tell you about OpenVM and its role in proving Ethereum for scaling the L1. So first, to set some context, Ethereum has embarked on this roadmap to scale L1 execution with zero-knowledge proofs. So to tell you what that means, the bottleneck in Ethereum execution today is that validators have to re-execute every transaction. And so what that means in particular is that they have to access the database for every storage read or write that a transaction makes. And this all has to happen within the slot time. And so what that means is that to increase the gas limit, we'd have to require validators to have ever more powerful machines, which risks centralizing validation and therefore the trust properties of Ethereum itself. So instead of doing that, Ethereum is embarking on a path to instead prove execution with a zero-knowledge proof and have validators verify those proofs. That is something that takes constant time, irrespective of the size of the block, and therefore can drop the load on validators while allowing the network to scale the gas limit. So this is going to take place over a series of steps which are laid out on the straw map. And to talk through the pathway, the goal is to have validators progressively move into this new way of block validation. So the hope is in Hagota, validators will verify optional proofs of execution in conjunction with the re-execution that happens today. And then in future forks, the re-execution can be completely removed and the gas limit can be increased, with validators handling the same load with just verifying zero-knowledge proofs of execution. Once that's done, the hope is that the same infrastructure can also be used to scale rollups by verifying their execution in a native rollup framework. Now, for all of this to work, we actually have to prove the blocks extremely fast. Now, there's a buzzword of real-time proving, but what this means is that validators have to receive a zero-knowledge proof of block execution within the slot time. So instead of each validator receiving the raw transactions in a block and re-executing them, often in less than a second in the slot time, the blocks will be sent from a block builder to a prover. The prover will gossip the resulting proof to all the validators, and then validators will verify that proof essentially instantly. Now, to do this, we have to be able to prove execution of an Ethereum block in zero knowledge. Now, obviously, Ethereum execution is quite complex, and so the most ergonomic way to actually do this is to use what's called a zero-knowledge virtual machine. So this is something that allows developers to generate proofs of ordinary computer programs. And the proof program we're interested in here is the state transition function of Ethereum itself. You might imagine this is very complex, and so as a result, we need to build quite a bit of machinery to be able to produce a ZK proof for it. Now today I want to talk to you about OpenVM, which is the ZK VM that allows us to actually do this. So we built OpenVM as a modular and performant approach to ZK VMs, prioritizing customization and extensibility. So to tell you a little bit about it, it's built on a novel no CPU architecture for the actual ZK circuits. What that means is that unlike most ZK systems that are a bit skeuomorphic to physical processors, we were able to take out the CPU component of the VM. And this allows different operations of the VM to be plugged in by developers as they need. In particular, it allows OpenVM to have modularity at the ISA level, supporting different types of operations in the ISA. And finally, it has a Rust developer front end, which means that as a developer, you can take any arbitrary Rust program and generate a proof of its correct execution using OpenVM. So to not bury the lead, we are now able to prove Ethereum in real time with OpenVM 2.0. So on a recent benchmark of 7,200 blocks, which is a full day of blocks, we're able to prove Ethereum with a P99 proving time of 8.5 seconds, an average time of 5 seconds, and in the sample, the highest time was 10.7 seconds on 16 5090 GPUs. So you can see the full histogram of proving times on the left, and notably, 10.7 seconds is less than the Ethereum slot time of 12 seconds. So we're definitely getting there on performance while only needing 16 GPUs in the cluster, which should enable users from around the world to participate in proving. Now, to give you a sense of the progression here, a little over a year ago, we proved block 21 million in something like 260 seconds. And since then, we've been able to lower that by over 60x to a little over 3 seconds, as you can see in the graph on the right. So this has progressed quite a bit on performance in the last year. In addition to proving Ethereum, we also evaluated our VM to prove a standard benchmark workload called CoreMark, which is used to evaluate embedded CPU performance for physical processors. Since we're proving arbitrary computer instructions, we thought this could be an appropriate benchmark for our ZK system. So in the blue, you can see our numbers from about a month ago, and in the red, these are our most recent benchmarks from our beta release in March. So on a single GPU, we're able to prove CoreMark at about 19 megahertz, and on a larger cluster of 64 GPUs, we can scale up to over 900 megahertz. So this is actually pretty close to the speed of some processors you might actually use today, which we think is very exciting to enable ZK proving of just ordinary computer programs that you might use in practice. And finally, on the performance side, we were able to power OpenVM with an ahead-of-time executor, namely something that runs the raw computer programs that OpenVM is proving. And this is a bottleneck in the proving because we're getting to the point where proving is get close to execution. And for OpenVM, our ahead-of-time executor actually runs the underlying RISC-V assembly at close to native speed at around 3.8 gigahertz. All right, to tell you a little bit about what's underlying OpenVM 2.0, we introduced a new multilinear proof system called SWIRL to power OpenVM 2.0. So it's based on WIR, which is a very efficient hash-based multilinear commitment scheme that enables extremely cheap verification. And with SWIRL, we're able to achieve 100-bit provable and post-quantum security while keeping the actual zero-knowledge proof size under 300 kilobytes. And so the proof size here is very important for participation in the Ethereum gossip network without increasing bandwidth requirements too much. And finally, because of this cheap verification property, we're able to power OpenVM with a very fast recursion that handles dynamic numbers of proofs. So this is important in the actual ZK aggregation process. And finally, obviously, ZK VMs are quite complex systems. There's a lot of ZK circuits. We have to deal with hardware ISAs. So as a first step towards ensuring a higher degree of assurance that will be necessary for use in the Ethereum L1, we work with Nethermind Research to actually formally verify the RISC-V front end for OpenVM in the lean theorem checker. So what this means is that we were able to prove formally the mathematical theorem that the implementation of RISC-V in OpenVM actually matches the official specification of RISC-V from the makers of RISC-V themselves. So this specification is used to typically verify hardware implementations of RISC-V, but in this case, we use it to verify the ZK implementation. We were relieved to know that during the process of the formalization, we didn't find any bugs in our implementation, and we hope to actually expand the scope of formal verification in OpenVM going forward. Okay, so I told you a little bit about the role of ZK in Ethereum's scaling roadmap and how OpenVM might play a part. So what's the implication for developers? I think there's probably two large takeaways. The first is that this will be a pathway for Ethereum to scale the gas limit on L1. Obviously, scaling gas lowers gas fees, reduces congestion, and critically, because the scaling will essentially be tied to the performance of ZK proving, increasing the performance of ZK even further will directly translate into the ability to scale the gas limit without compromising the security and decentralization properties that are critical to Ethereum. On the application front, ZK can be used outside of the L1, of course, and we think it's really exciting to have performance ZK at the application level. To mention a few possible directions, ZK can be used to generate validity proofs for rollups, to validate the execution of complex off-chain operations, and finally, to add certain privacy and verifiability features for more institutional use cases. All right, so I'm from Axiom, which is the company behind OpenVM. So we're working with applications to explore these more application-focused use cases of ZK. So we help people design applications with the knowledge that ZK is possible, accelerate them with custom extensions to OpenVM to make ZK even more performant, and finally, to actually generate the proofs on our API. Some examples of teams we've been working with are Lighter, which is adding EVM support to their verifiable exchange, SWIRL, which is using OpenVM to actually verify their rollup for the past year, and a similar ZK-enabled perpetuals exchange on top of Hyperliquid. And OK, great. So that's my last slide. So you want to learn more about OpenVM, you can check out our docs, our Telegram group, or the code on GitHub. If you're interested in working with us to add ZK into your application, you can check out the link on the slides. And I have some time for some questions.
So does anyone have a question?
Can you just say a few words on what are commitment schemes that you're using and how much it differs from other proving schemes like Plonky 3, for instance, that is quite popular around, or Stark in general?
Yeah, it's a great question. So we're using the WER polynomial commitment scheme, which is a hash-based commitment scheme that's adapted for multilinear polynomials. So Plonky 3 actually recently added support for WER in addition to the previous Fry commitment scheme, but we're not using the Plonky 3 implementation. So we wrote our own implementation.
And it's open source?
Yeah, everything's open source, MIT, Apache 2.0, dual licensed. I should put that in the slide.
All right, great. So no more question.
Cool, thanks everyone.